So this week, we are switching gears a little bit, still looking at hypothesis testing, but we're looking at testing now the difference between the parameters of two populations. Now, it could be, most of the time, what we're going to be doing is independent samples from different populations. But there is one process we will do that is matched samples, what we call paired samples, a paired test, in which there's actually a link between the two samples. They're not necessarily independent. We'll look at that when we get to it. So what we're going to start off with is talking about the difference between two population means. So the means of two populations. And the way we're going to measure that, our estimate, a point estimate, is going to be I have to draw this out with my finger. We're going to take a sample from the first population and calculate its mean. That'll be x bar 1 minus, we'll take a sample from the second population and calculate its mean. That'll be x bar 2. Well, that'll be our point estimate for mu1, which would be the actual mean of population 1, minus mu2, which would be the actual mean of population 2. Well, and it actually works out that when we look at the distribution of the sampling distribution of this, the sampling distribution of x bar 1 minus x bar 2 has a mean. So the mean of that sampling distribution, x bar 1 minus x bar 2, is actually equal to just the difference in the population means. So what that tells us, what that means for us, is since this distribution of the difference of the sample means is centered on the difference of the population means, it's telling us that this is an unbiased estimator of that difference of means. So we can use the difference between two sample means in the process of estimating here. Now, the standard error of those means, we said that the sampling distribution is centered at the difference of the population means, but that sampling distribution has a spread. And remember, the spread of that sampling distribution, standard deviation of the difference of the sample means. Again, this is often called the standard error, is given by, of course, the symbol, that's the standard deviation or standard. So we get back to a normal color here. So that sigma is the standard deviation of the x bar 1 minus x bar 2 is equal to the square root of the standard deviation of population 1 squared divided by the size of the sample from population 1 plus the standard deviation of population 2 squared divided by the size of the sample from population 2. Now you see sigma squared is the symbol used for variance. Now the square of the standard deviation is the variance. So Some textbooks say that we're using the variance there rather than the standard deviation squared. It means the same thing. It's the same number. You know, we had mentioned at one point that in many of our more complex tests, we use the variance rather than the standard deviation. Here's really an example of that. Now here we used, this is the case if we know both population standard deviations. And of course, if we know both population standard deviations, it's going to be a z-test. In fact, on the calculator, they call it a two-sample z-test or two-samp z-test. Because it's two samples to test the difference between two population means. If we do not know both population standard deviations, which is usually the case. In fact, Minitab doesn't even have an option for knowing the standard deviations when it's a two sample test. It just puts you straight to the standard deviations being unknown. So if that's the case, it'll be a t-test. In fact, it's called a two-samp t-test in the calculator. And we just change our standard error our estimate of that is just going to become the sample standard deviation squared over the size of the sample from population 1, and the sample standard deviation for the sample from population 2 over the size of the sample from population 2. We substitute those in. Now our test statistic don't worry, I'll get to some examples soon. I realize I'm throwing a lot of information here up front. Our test statistic, if we know both standard deviations, it's a z-statistic, and that would be x bar 1 minus x bar 2, the difference in the sample means, minus mu1 minus mu2, the difference in the population means. Now, we don't know this number. That's what we're trying to estimate. So since we don't know that number, we use our hypothesized value from the null hypothesis. Over, of course, that'll be our standard error, the square root of. Now, if this is z, so we would have our population standard deviations. So it'd be sigma in there. If we do not know population standard deviations, our test statistic for a t-test, t will be, let's go pretty much the same, x bar 1 minus x bar 2 minus mu1 minus mu2. Again, we won't know these values for mu, so we're going to use what we hypothesize in the null hypothesis. And all that changes is our standard error is now we use the sample standard deviations instead of the population standard deviations. One complication with this, because the t-distribution, excuse me, requires us to calculate degrees of freedom. In a single sample situation, the degrees of freedom was just the size of the sample minus 1. It's not so simple when we have two samples and we're combining them together. So our degrees of freedom here, I don't know if I'll, let's go to another page just in case. So our degrees of freedom are going to be standard deviation of sample 1 squared divided by the size of sample 1 plus the standard deviation of sample 2 squared divided by the size of sample 2. And then that whole thing is squared divided by standard deviation of sample 1 squared divided by the size of sample 1. That gets squared and divided by the degrees of freedom in sample 1. So that's just the size of sample 1 minus 1. Plus the same thing for sample 2. Standard deviation of sample 2 squared divided by the size of sample 2. That ratio squared over n2 minus 1. These degrees of freedom, one of the few times where we always round down. Everything else we've done, sample size calculations, position for percentiles and stuff like that, have always been rounded up. This needs to be rounded down. The reason being is fewer degrees of freedom gives us a wider interval or a wider net. So it reduces our chances of rejecting the null hypothesis. And remember, these hypothesis tests are stacked in favor of the null hypothesis. The null hypothesis is the statement that we want to keep unless we're faced with tremendous evidence against it. So we round down our degrees of freedom in order to make sure that we're keeping that safeguard in place, making sure that we're not increasing the chance accidentally of rejecting that null hypothesis. Now, if you're using technology, this is a long calculation. If you're calculating it out by hand or even with a calculator, you really don't want to go through that process very often. So if you're doing this without technology to run the test for you, there is an estimate that saves a lot of work. And it is called pooled variance or pooled standard deviation. And it's just a process of combining the standard deviations from the two samples and then using a standard number of degrees of freedom rather than doing this calculation here. It's an estimate. And just like rounding down, it actually casts our net out even further, makes it even less likely to reject a null hypothesis. But it saves a lot of work. Now, in our case, we have the technology available to us. We're going to be using the calculator or Minitab. So there's no reason for us not to do the regular degree of freedom calculation here. I see some chat sessions coming. Oh, no, just people coming in. Okay. So let's actually look at our hypotheses and how our hypotheses get worded. The null hypothesis, I'm just going to use U for mu. H0, the null hypothesis is always going to be mu1 minus mu2 equals some hypothesized value. Whether it's 0 difference or whether there's a minimum difference or maximum difference that's being defined. That's always our null hypothesis. The alternative hypothesis then, HA could be that mu1 minus mu2 is not equal to that hypothesized value. Of course, this is a two-tailed test, which means we reject if we get a test statistic or value from our samples that's either too small or too large compared to that hypothesized value. We could have an alternative hypothesis that mu1 minus mu2 is less than that hypothesized value. And of course, this is a one-tailed test. It is a lower or left tail test. lower tail is smaller values, meaning if we get a value for the difference from the samples that's too small, we will reject our null hypothesis. And finally, our alternative, mu1 minus mu2, is greater than the hypothesized value. Still a one-tailed test. However, this is now an upper or right tail test. Some textbooks allow for the null hypothesis to be worded as mu1 equals mu2. And the alternatives as rather than the difference is different. Of course, this would be mu1 not equal to mu2. This one here, mu1 minus mu2 is less than the hypothesized value. That's actually saying that mu1 is less than mu2. This is actually saying mu1 is greater than mu2 by more than the hypothesized value. Now, the problem with these is that these only work if the null hypothesis is saying they're equal. In other words, that's saying the hypothesized value of the difference equals 0. And we don't want to always do that. This is just kind of an oversimplification here of the hypotheses. But it does help us view what this, mu1 minus mu2 is less than the hypothesized value, is telling us that mu1 is either smaller than what we expected or mu2 is larger than expected. The other way here, mu1 minus mu2 is greater than the hypothesized value, is telling us that either mu1 is larger than expected or mu2 is smaller than expected. So keeping these in mind helps us kind of interpret what those hypotheses are. But in general, we can't use those really. There's oversimplification only in the case that the hypothesized difference is 0. Okay, enough theory and background. Let's do some examples. So for our first example here, we have an ACT prep company claims their program will increase ACT scores by at least 2 points. So independent random samples were taken. From students who did not use the prep company. We'll say the prep program, and those who did. For those who did not use the prep, a sample of 45 students gave a mean score of 19.2 with standard deviation of 2.7, it looks like. For those who did use the company, the prep, a sample of 40 students gave a mean score of, let's go 21.9 and standard deviation of 2.4. Test at alpha equals 0.05 to see if we can see if there is evidence to support the prep company's claim. So first we got to set up our hypotheses. The null hypothesis is that the mean difference in this case is, let's see, mu1 is the people that did not take the prep. Mu2 is for those that did take the prep. So that'd be a -2. The alternative is that mean difference is less than -2, meaning they were more than 2 points less if they didn't use the prep program. So let's enter this in the calculator, see what we come up with. First of all, our standard deviations both came from samples. So we're not using a z-test here, we're using a t-test. So we go to stat, tests, and we see right here, 2 sample t-tests, option number 4. Now we have our inputs here. We can either do data or stats. We're going to do stats here because we have the summary statistics from our sample, not the individual values from each sample. X bar 1, this is the mean of our first sample, is 19.2. As SX1 is the standard deviation of the first sample, that's 2.7. And 1 is the size of the first sample, which was 45 students. X bar 2 is the mean of the second sample, that's 21.9. The standard deviation of the second sample is 2.4. And the size of the second sample is 40. Now, as we go down here, we're going to get asked for our alternative hypothesis. It's less than. Notice the calculator uses poor terminology here. It's saying mu1 not equal to mu2, mu1 less than mu2. It still means the same thing. Less than still means mu1 minus mu2 is less than the hypothesized value. It's just using poor terminology on the calculator here. Now, this is what we discussed. Do we want to pool it and take a shortcut? Well, the answer here is always no. If the calculator is doing the work, we want to do it the precise way rather than taking a shortcut and doing an estimate. So pooled is always no. And we'll hit calculate. We get a test statistic here. Let's go find my pen. Of t equals -4.88 with a p-value of 2.52 e -6. So I want to do 2 things. I want to interpret this and tell you what that p-value means. So let's get back here. So our test statistic, t, is a -4.88. That's a pretty, remember, the further we are away from 0, the larger our test statistic is. That's a pretty large test statistic. It's a long ways away from 0. Our p-value of 2.52 e -6. Remember, that's really 2.52 times 10 to the -6. So that's actually 0.0000252. 0.0000252. In other words, pretty much 0 for a p-value. The p-value, remember, tells us what is the probability, what's the consistency between our sample and our null hypothesis. This is saying the consistency is almost nothing. Saying the probability of getting a worse test statistic if the null hypothesis is true is very, very small. It's almost nothing. So because the p-value of 0.0000252 is less than alpha of 0.05, we will reject the null hypothesis. So that is our conclusion of the test, or our statement of rejection, I should say. Our actual conclusion, then, we talk about what does that mean for the alternative. That means there is sufficient evidence to claim that students score at least 2 points higher after using the prep. So we didn't prove the company's claim, but we showed that the alternative to the claim, the null hypothesis, is highly unlikely. So we rejected the opposite of their claim, which means the only thing possible left is to take their claim, in favor of their claim. Like I said, we're not trying to prove anything here. We're not collecting evidence in support of anything. We're trying to collect evidence against the null hypothesis. And we did manage to gather enough evidence against this null hypothesis that we rejected it, which means the only other possibility is the alternative. So we didn't prove the alternative, but that's all that's left. That's the only option that's left. Let's look at another example here. Where'd my mouse go? There it is. So for this example, we have two cities. City A claims their mean hourly wage is higher than City B. It is known that the standard deviation of wages in City A is $1.94 per hour, and in City B is $2.04 per hour. Independent random samples are taken. A sample of 60 workers from City A gives a mean of 18.02 per hour. A sample of 70 workers from City B gives a mean of 17.99 per hour. So we're going to test City A's claim. Let's go alpha equals 0.10. We'll make a pretty loose test here. So our null hypothesis is that the mean 1, which is City A, minus mean 2 equals 0. There is no difference. The alternative is mean 1 minus mean 2 is greater than 0. That's saying City A is larger than City B. So let's enter this information into our calculator. So clear this out. Now here we were given the population standard deviation. So we go to test. This is a 2-sample z-test because we know both population standard deviations. We are again using the summary statistics from our samples. Our first standard deviation is $1.94. That's actually in there from last night, apparently. The second standard deviation, population standard deviation, is 204. The first population mean is 18.02 from a sample size of 60. The second population mean is 17.99 from a sample size of 70. The alternative here, we want greater than is our alternative. And it doesn't ask about pooled because remember, we don't need degrees of freedom for a z-test. So we're just going to hit calculate, and there we go. So z is 0.086 with a p-value of 0.466. So let's analyze this quick. Let's break this down. So our test statistic, z here now, is a positive 0.086. And our p-value is 0.466. Now our test statistic being positive says that our sample value for A was larger than the sample value for B, but it was not large enough to conclude that there was actually a difference. It wasn't big enough to override the possibility of just being random variation in our sampling. So our claim here, our conclusion here on the test is, since the p-value of 0.466 is not less than alpha of 0.10, we fail to reject the null hypothesis. There is not sufficient evidence to conclude that city A's wage is higher than city B's. Now, I want to go back to both of these examples and talk about confidence intervals. First of all, what confidence interval would correspond to the test? This test is a one-tailed, lower-tailed test. Down here, it's alpha of 0.05, so that means that 0.05 of alpha is all on the lower tail. To do a confidence interval that would correspond to that, we would still need 0.05 on the lower tail. But a confidence interval always comes right out of the middle. So that means there has to be 0.05 on the upper tail as well. So the confidence interval that would correspond to this test here with alpha of 0.05 is a 90% confidence interval. So let's do that right now. We're going to construct a 90% confidence interval for the difference in these population means. So let's go to the calculator and enter this information here. So we're going to go to stat, tests. Now we have to go down to, this is a t interval, but it's a 2 sample t interval. There it is right there, option 0, 2 sample t interval. Using our stats, our first mean is 19.2. With a standard deviation of 2.7 and a sample size of 45. Second mean was 21.9 with a standard deviation of 2.4 and a sample size of 40. Confidence level is 0.9, 90%. Pooled, we're going to stick with no, let the calculator do the hard work. And let's calculate. So I get an interval here of negative 3.62 to negative 1.78. Now, let's talk about what this means here quick. I don't know why this did not. Well, let's talk about what it means. This should have supported our hypothesis test up here. The hypothesis test said the difference is definitely more than 2 points, at least 2 points higher. However, we got a confidence interval here, and there is sometimes a little bit lost in translation in the confidence intervals, but that went from a negative 3.62 to a negative 1.78. Our hypothesized difference in the null hypothesis was -2. That's in this interval. If that value from the null hypothesis is in the confidence interval, that generally indicates that we cannot reject the null hypothesis, because that's saying that the null hypothesis is possible. So something here went wrong in the translation between our, I'm guessing it's the translation because this is a one-tailed test, that it didn't translate perfectly into a confidence interval, which happens. If it's a two-tailed test, this will always be the exact same conclusion. Well, let's look at this one here. Let's construct. This was alpha of 0.10, and this was also a one-tailed test. So that means this is upper tailed. So that alpha of 0.10 is all on the upper tail. So for the confidence interval, we have to have 0.10 on the upper tail. And since the confidence interval comes out of the middle, we'd have to have 0.10 on the lower tail, which means this is only going to be an 80% confidence interval to track this. So let's do that. Let's find the 80% confidence interval. For the difference in population means. So let's enter this back in the calculator. So stats, tests. We're going to go down to two sample. This is a Z interval now because we do have both population standard deviation. So two sample Z interval. Our first standard deviation is 1.94, second is 2.04. First sample mean is, what do we have, 18.02. Sample size was 60. Second sample mean was 17.99. Sample size there was 70. Confidence level is going to be 80%, so 0.8. We calculate, and we get negative 0.418 to a 0.4. We're going to round that to 0.478. Let's talk about what this means. So our interval goes from negative 0.418 to a positive 0.478. The biggest thing we want from this is that 0 is in this interval. Our hypothesized difference from the null hypothesis was 0. It's in this interval. So this supports our conclusion to fail to reject, because this confidence interval is telling us that hypothesized value is very possible, because it's in this almost in the center of that interval, to be exact. Now there's another type of test for population means, and that is a matched or a paired sample test. What this does is, rather than taking the complete samples, finding the means of each sample and subtracting the means, we have two samples, but the items in the samples are paired up, and we calculate the difference between the values for each of those pairs. And so we test the differences. The set of differences is what we test. Now there's two different ways this can be done. Either we can use one sample with two different treatments. This is usually like a before and after type test for blood pressure medication. Blood pressure before taking the medication, average blood pressure after being on the medication for 4 weeks. And we'd test the difference. Did it go up or down or stay the same? The other is to have some sort of logical pairing between the samples. This is why twins are so important to medical research, because if they're maternal twins, they should have exactly the same genetics. If they have exactly the same genetics, then they should react exactly the same way to a medical treatment. So we split them up and we give them 2 different medical treatments. If the medical treatments are equivalent, they should react the same. So since their genetics are are identical, any difference in their reaction must be caused by the treatment rather than by their genetics, by their makeup. Now there's some ethical issues there involved with that. So it's not done as often as it used to be, but there are still ways we can logically pair things. For example, a coach claims that his team, I should say a football coach, that his team has outscored opponents by more than 12 points per game on average over the last 5 seasons. A random sample of 12 games is taken, and the scores are recorded. Home team, which is the coach, and opponent. So here are those scores. First game, 45-14. Second game was a win, 21-14. Third game was a win, 35-24. Fourth game was a win, 31-28. Next game was a win, 38-21. Next game was a win, 20-3. Game 7 was a win, 34-24. Next was 42-31. Next was 41-28. Next game was 27-10. Then we had 20-14, and the last game selected was actually a loss, 18-20. Now, our hypotheses here, the null hypothesis is going to talk about the difference. It's saying the mean difference is equal to 12. The alternative will be that the mean difference is greater than 12 to support the coach's claim. Now, so what we're actually testing here is the difference. So like for the 45-14, we'd subtract, that's a difference of 31 points. 21 minus 14 would be a difference of 7 points. 35 minus 24 would be 11 points. 31 minus 28 is 3 points. And we would go do those differences all the way down the line here. It's actually that set of differences that we're testing. Now, we don't actually have to calculate those differences ourselves. This last one, since it was a loss, would be a negative difference, a -2. We can use the calculator to do that calculation. Let me show you how. So now we're going to go to Stat. We're going to go to the Edit menu, and we're going to select Edit, which is going to take us to our data lists. If we want to clear out a list, you highlight the heading at the top of the list. You just do clear and enter, and it clears out the whole list. Now, I actually already have my home team scores entered in list 1. Now, the first game was 45-14. See the home team scores in list 1. The opponent is in list 2. And so all the home team scores are in list 1. All the away team scores are in list 2. Now, to calculate the difference, here's what I'm going to do. I'm going to go to list 3, and I'm going to arrow up and highlight the L3, the title at the top, and I'm going to enter a formula. What I want to enter here is I want to take the L1, the home team score, minus L2, the away team, the opponent's score. So I'm going to do second 1 is L1, minus second 2 is L2. That's saying for each entry, take the entry of L1 minus the entry of L2, put that into list 3. And there it goes. It calculates those differences that I just calculated on the other page. So what we're testing is this list here of differences. So we're going to do second, quit to get out of the lists. We'll go to stat, tests. And now this is just a simple t-test. We only have one data set. We're not doing 2 samples. We are using the data though. Our data is in the list, so we select the data option. Our hypothesized difference is 12. Our data is in list 3. Now, if that says list 1, you just do second, 3, and it's going to bring it to list 3. Frequency always gets left at 1. The frequency, anything other than 1 is for more advanced tests where the data is being repeated more than once. We're going to leave that at 1 always for everything we do. And then, of course, our alternative here is greater than. The coach said that they outscored them by more than 12 points. So we're going to calculate. We get a test statistic here of a negative 0.1028 and a p-value of 0.54. Let's analyze this. So our test statistic T is a negative 0.1028 with a p-value of 0.54. 0.00 actually. So here, since the p-value of 0.5400 is not less than alpha, I guess I didn't name alpha up here. Let's test it. Alpha equals 0.05. Since it's not less than alpha of 0.05, we fail to reject HO. So this means there is not sufficient evidence to support the coach's claim of winning by more than 12 points on average. So we were not able to give the coach any support there with that test. In fact, if you look at the calculator, the mean difference was actually 11.75 for the sample, not a 12. So we were well below it as far as the test is concerned. We're a little short of time, so I'm not going to do the confidence interval here. The confidence interval here is just a simple t interval. Well, we got a second. I won't type it in, but let's just do a 90% confidence interval on that set of data. So stat, tests, I believe it's option 8, which is a t interval. It's just a simple t interval. There it is. We would use the data, list 3. Let's do a 90% interval here, 0.9. And there's our interval. Now 12 is in that interval, which is saying, remember the null hypothesis said the difference was 12. So since 12 is in that interval, it supports that idea that the null hypothesis is possible, so we can't reject it. We need to talk a little bit about proportions. Sorry about the tests for the difference between 2 proportions. So our the mean of the difference of the proportions, so p hat 1 minus p hat 2, is going to be equivalent, is going to be centered, that distribution is going to be centered around the difference of the population proportions. The standard error So sigma of p hat 1 minus p hat 2 is going to be the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. There are some strategies to ease up some of our tests, and in certain cases where we can pool or find a common population proportion. That's p hat common. The way the textbook writes it out is to use n1 p1 plus n2 p2 over n1 plus n2. But realistically, n1 times p1, that's just our x1. n2 times p2 is just our x2. So it's really just x1 plus x2 over n1 plus n2, where x1 is those that the affirmative, the yeses from each sample, and n1 is the size of each sample. Well, let's look at an example here. Let's get away from all the background information. So our example here, a dean believes that sections of statistics that use an online, excuse me, homework practice system have a higher pass rate than sections that do not. So independent random samples are taken, a sample of 250 students in sections using an online system gives 203 pass. A sample of 230 students, oops, 30, not 40, in sections not using an online system gives 183 that pass. We're going to test the dean's belief at alpha equals 0.05. So our null hypothesis is that P1 minus P2 equals 0. There is no difference. The alternative, P1 minus P2 is greater than 0. That those who used it had a higher pass rate. Let's go to the calculator. So clear this out. We're going to go to stat tests. Now this is a z-test, but we want to use the proportion test here. So this is a 2 proportion z-test. Our first proportion, x1, was 203 that passed. n1 was out of 250. For the second sample, we had 183 that passed out of a sample size of 230. Our alternative hypothesis is greater than, so we select that and we'll hit calculate. So we get 0.451 and a p-value of 0.326. Let's look at what this says. So our test statistic, z, is 0.451. Now that is positive, so it is indicating that P1 in our sample was larger. But the p-value tells us how consistent it was. It's 0.326. That's a high p-value. It's saying it's pretty consistent that if the null hypothesis were true, that there is no difference, pretty good chance of still getting a difference as large as what we had. So since the p-value of 0.326 is not less than alpha of 0.05, we fail to reject the null hypothesis. There is not sufficient evidence to support the claim that students have a higher pass rate when using an online system. So that's all of our tests here. Let's take a peek. I want to do some look at Minitab. So let's take a look at Minitab here. Now for this, as I mentioned last week and for this week as well, I think the calculator does hypothesis testing better than Minitab, better than Excel. So anything on the application assignment where it asks you to use Minitab, I'm okay with you using the calculator or Excel, just as long as you put down, what's your test statistic, what's your p-value. If you use the calculator, to help you know what command you use to make sure if your numbers are slightly off, I can tell if the problem was you used a z-test instead of a t-test or whatever. But as long as you put that information down, I'm okay with you just using the calculator, because I think it does a better analysis, easier to interpret analysis than Minitab does. Where Minitab might be slightly easier to use is if we have our data in lists. Typing lists of data into the calculator is kind of tedious, but we can very quickly copy and paste into Minitab. So let's look at our two cities again, city A and city B. This time we have their wages listed out. So our null hypothesis here, I'm going to put down as mu1 minus mu2 equals 0. There is no difference. The alternative, mu1 minus mu2, is greater than 0. We're going to say that city A has a higher wage. We're going to test at alpha equals 0.05. So let's take a look at how this all gets done in Minitab here. First, we're going to go to Stat, Basic Statistics, and we're going to select two sample. Now notice it has one sample Z, one sample T, but for two sample, it only has the t-test. It doesn't even give that possibility that both sample standard deviations. Now we need to select our input. Both samples are not in one column. Each sample's in its own column. First one is city A and city B. Let's select our options. Alpha is 0.05, so 95% confidence is correct. Our hypothesized difference is 0. Our alternative, however, is greater than. So we're going to select that and hit OK. So those are hypotheses. We get a p-value of 0.174, which is telling us we do not reject the null hypothesis. We cannot, there's not enough evidence to conclude that city A is greater than city B. Now notice it does not really give a confidence interval up here. To get a confidence interval, we have to use the alternative hypothesis of not equal to. Now going from two-tailed to one-tail, we have to switch this to 90 because that 5% on the tail is going to be now in both tails now for the interval. And so here we get that confidence interval. It goes from a negative 0.573 to a positive 2.08. That supports 0 is our hypothesized value from the null hypothesis, and 0 is in that interval, so that supports the fact that the null hypothesis is possible, so it can't be rejected. A little more clumsy is if we use Minitab for summary data, where we have the summary of the sample data and we want to enter it. Let's look at this. Let's use GoACT and ACTU. And let's say we're going to use a sample size here. GoACT, where we get 4 customers that use them for ACT prep. And we found a sample of 51 customers that used ACTU. The mean score for GoACT was 23.8. ACTU was 24.1. Standard deviation, 3.2 and 3.5. Our hypotheses here, H0, we're going to claim mean 1 minus mean 2 equals 0. The alternative, we want to claim that ACTU is better. So mean 1 minus mean 2 is less than 0. That's saying the second one's actually bigger. And we'll test at alpha equals 0.10. So up here we go to stat, basic statistics, to sample again. Now we got to select our input. We have summarized data. So our sample size here is 48. This sample size is 51. Mean of 23.8 and 24.1. Standard deviation 3.2 and 3.5. Let's select our options. This is going to be a 90% alpha of 0.10, so 90%. Alternative hypothesis here is going to be less than. So select less than. We hit OK and go. We get a p-value of 0.328, so that's saying we failed to reject. That is not less than alpha. So there's no evidence to claim that ACTU is better or produces higher scores. Again, we don't have a confidence interval, so we could go back and get a confidence interval by changing this to not equal to, and of course adjusting this to 80%. And there's a confidence interval. 0 is in that interval, so that's telling us that our null hypothesis, that hypothesized value is 0. So it's saying it's correct to not reject it because that value of 0 is very possible. For proportion, let's say we were getting supplies of parts from suppliers, and we think we're getting a high rate of flawed parts from our current supplier. So we get a sample of parts, a random sample of 40 parts from a new supplier. And we take a random sample of 40 parts from our current supplier. And our null hypothesis is that P1 minus P2 equals 0. The alternative is that P1 minus P2 is going to be greater than 0, that the potential new supplier has a higher rate of acceptable parts. We're going to test at alpha equals 0.05. So let's run this test. Stat, basic statistics. Now we have two proportions we're going to use in separate columns. This is going to be supplier A and supplier B. Our options, we're going to do 95%. So yes, alpha is 0.05, so 95%. Our hypothesized difference is 0. Difference, the alternative is going to be greater than. And we'll just leave that the way it is. Estimate the proportions separately. We're not trying to do any shortcuts. We're going to leave it as that standard setting. We hit OK. Here we get a p-value of 0.013. That is definitely less than alpha. So we reject HO. And the conclusion here is that there is sufficient evidence to prove that the new supplier has higher quality parts. Okay, so enough with Minitab. Let's get to the meat quiz. So, oops, something didn't go right there. Let me try that again. Here we go. So Franklin University wishes to compare two statistics professors. They select random samples of students from each professor's class. So we got the numbers from Professor A and Professor B. Now I'm going to tell you this much just to make it easier on you. That for the test, our hypotheses The null hypothesis is that the means, sorry, we're looking at pass rates. The pass rates are equal. The alternative is that the pass rates, oops, come on, are not equal. So P1 minus P2 equals 0, or P1 minus P2 does not equal 0. So I'll give you about 3 minutes here, and 7:06, so we'll go over these at 7:09. Come up with the 90% confidence interval and test at alpha of 0.05. Okay, so I realize, just a few minutes. These are kind of long procedures to do in just a few minutes. But let's take a look. Let's enter this information in the calculator and see what we get. So we're going to start out with a confidence interval. So stat test, and this is a 2 proportion Z interval. So option B here. Our first sample, we had 117 pass out of 132. Our second sample, we had 98 pass out of 107. Our confidence level was 90%, so 0.9 is correct. We hit equal, and there we go. We had a negative 0.0929 to 0.0338. Set confidence interval, negative 0.0929 to 0.0338. Now that says something about our upcoming hypothesis test anyway. Well, let's go ahead and do it. Let's do this calculation for our hypothesis test, see what we come up with. So on the calculator, stat tests. This is a 2 proportion Z test, option 6. Our information copied over from the confidence interval. Our our alternative hypothesis is going to be not equal to. So hit calculate. We get a Z score of a negative 0.755 and a p-value of 0.4502. So our test statistic here, it is a z-test because it's proportions. Oops, get back. So our z-score, test statistic, is a negative 0.755 with a p-value of 0.4502. Since the p-value of 0.4502 is not less than alpha of 0.05, we fail to reject HO. In other words, there is not sufficient evidence to claim there is a difference between the professors. Now our confidence level up here, oops, our confidence interval disappeared on us here. We'll put that back in. Our confidence interval up here supports that because our hypothesized value in the null hypothesis of the difference is 0, and 0 is in the confidence interval. That supports that the null hypothesis is possible and cannot be rejected. So our confidence interval and our test agree with each other. Okay, now that is all the new material we have for this week. If you need to get going, I totally understand. I want to take a second to go over, if anybody has time, a topic from last week that had a lot of questions. First of all, are there any questions on the material we just covered? Okay, and I'm sure they'll come up as we go through. There's a lot of stuff there, but that's good that you guys feel good for now. So what I want to cover from last week is the beta and power of a test. And I'm just going to do it with an example. So the example I'm going to do is, let's let U be the mean, mu, I should say, be the mean GPA for football players. Suppose the standard deviation of GPA for all football players is known to be 0.6. The coach claims his players have a mean GPA of 3.0 or better. So our hypotheses here, the null hypothesis would be that the mean is equal to 3.0. The alternative, the coach's claim, or would be trying to refute the coach's claim in this case, is that the mean is less than 3.0. A sample of 36 players is taken. Test the coach's claim at alpha equals 0.05. Now, first, alpha is very important here for establishing the power of a test because we have to find our critical value of z. So here's our bell curve. Our alternative is less than. So that means alpha of 0.05 is a lower tail because it's a lower tail test. So we need to find that corresponding z-score. We're going to go to the calculator here. That corresponds with 0.05. So we're going to go to second distributions, inverse normal, 0.05. And of course, this is going to be standard normal. So mean is 0. Standard deviation is 1. It gives us a negative 1.645. Is that critical value? So now let's say that the sample, actually what we're going to say is suppose The mean GPA is actually 2.8. Find beta. So what we do is we first find the z-score of 2.8. That's going to be 2.8 minus the hypothesized value, 3.0, divided by our standard error. So it's a standard deviation of 0.6 divided by the square root of our sample size of 36. This gives a z-score of negative 2.0. So our beta is found by doing a normal CDF of less than our z-score here for this value. It's less than because the alternative hypothesis is less than. So this will be negative 1 EE99, comma, negative 2.0. But now instead of using a standard normal distribution, we slide our mean over to be our critical value, the negative 1.645. We still use a standard deviation of 1 like we would with a standard normal distribution. So we're going to do second distribution, normal CDF from negative infinity, that's already entered in there, to negative 2. For our mean, we're going to do negative 1.645. And we're going to keep our standard deviation at 1. We get 0.3613. So 0.3613 is beta for this test. So the power is simply 1 minus beta. So 1 minus 0.3613 equals 0.6387. That is the chance that 0.6387. That is the chance that we will reject the null hypothesis if it's incorrect, based on the information we have. Hopefully that clears up some of the questions on that from last week. Okay, so any questions on anything that we've covered tonight? Okay, well, as they come up through the week, please send me an email.